Welcome to the instructional video for the NCDOT Lifecycle Cost Comparison Tool, version 1.0. The spreadsheet-based tool is designed to be used during the planning phase of potential intersection conversion projects. This tool can be used to project the long-term costs and benefits of converting two-way stop control intersections to three other intersection control types: all-the-way stopped, signalized, and roundabouts. The outputs of this tool include projections of the dollar values of construction and maintenance, safety, and delay associated with different conversion options. However, the outputs of this tool should not be the only information used when making a decision about converting an intersection. This tool has 8 steps organized by input and variable type. Each has its own spreadsheet and tab as seen below. To move between sheets, the user can click a Proceed to Step button to move to the next step, or Return to Step button to go back to the previous step to make a change. All steps should be completed by the user in the order that they occur. A failure to follow steps in order could result in miscalculations or data loss. Before using the tool, a few items should be considered. Throughout the tool, different colors can indicate different types of inputs. Light blue cells include descriptions of input or output cells, such as the yellow cell here. Yellow cells indicate that the user must either fill in a blank cell or must adjust cells with drop-down boxes. Green cells indicate that the tool provides predetermined default or standard values, as seen on the defaults page. These values should only be changed by an authorized staff member with a password needed to do so. All units, if applicable, are shown in parentheses next to each input or output field, as seen here with service life. Users are strongly encouraged to collect and calculate the site-specific data needed for inputs before beginning the analysis process to reduce the risk of error. The data required is listed at the beginning of the instructions for each step in the user manual. Users are advised to save the file they are working on each time with the analysis date and site name immediately upon beginning an analysis in order to prevent calculation errors. Files should be resaved after performing any additional analyses or revising inputs. The first step in the tool is called Global Inputs. This step requires that the user provide basic information, in these yellow cells here, about the current two-way stop control intersection. The first input that must be made is the name of the intersection. For example, A street and B street. Second, the county that this intersection is in can be listed, for example, Wake County. Then the analyst name. In this case, I will enter Jane Doe. And then the main approach orientation can be chosen by clicking this drop-down box. So, for example, if your main line is going east to west, we would select that one. If it was north to south, you would select that direction. This input is especially important because so many of the delay calculations depend on identifying where the main approach is versus the minor approach. Next, the analysis date, so the date that you're actually entering the data, will need to be added. Then the actual number of the NCDOT division. So in this case, since we're in Wake County, that would be 5. The next entry requires that you, again, select an option from the drop-down box. In this case, we do not have a two-way stop control intersection that has a median with a width of 20 or more feet. So I'm going to answer no. If you did, you would answer yes. Then you'll need to enter the operational analysis period. So for example, my operational analysis period is 20 years. That means I'm looking 20 years into the future from today to see how those costs and benefits are going to accumulate for each of the alternatives. The tool only allows the user to input a minimum of 10 years and a maximum of 25 years for a variety of reasons. Then the volume of growth factor per year must be entered. The NCDOT recommends that the volume growth factor be between 2 and 3%. However, if the user is aware, for example, that there is a significant amount of data showing that a large development is going to be built in the next 5 years and wants to put a higher volume growth factor, they can do that. And there's an opportunity for the user to put feedback about that decision in the final report of the tool. So in this case, I'm going to put the standard value of 3%. Next, the current percentage of heavy vehicles will need to be entered. In this case, we're going to say that it's 5%. And this is the current percentage of heavy vehicles that are occurring at that particular intersection. Next, the peak hour factor will need to be entered. In this case, I'm going to put 0.9. And then the area type can be selected by choosing from this drop-down box. So this is the area type for the current two-way stop control intersection. So you can select either urban, suburban, or rural. I'm going to select rural for this example. And finally, the current unleaded and diesel fuel costs for today, so today's date, will need to be entered. You can find these by going to this link here on AAA.com. And this comment box will show you that. For the sake of example, I'm going to pretend that the unleaded fuel cost is $2.15 and the unleaded fuel cost is $2.25. Once all these yellow cells have been filled, the user should look closely at each of their entries to ensure that they're correct. These entries are especially important for the calculations of the tool and will greatly impact the outcome of the tool. But when the user is happy, they can click Proceed to Step 2 to move to the next step. The user, before moving forward, can also click See Default Values. Clicking this button takes you to a separate page that shows the various variables in the tool and the standard values that are used for those in the processes of the tool. All of these are based in research and communication with the NCDOT, and their sources can be seen by clicking these little comment sections with the red triangles. Now, these values, because they have been so heavily researched, can only be edited by a person who has administrative power to do so. We highly recommend not changing these unless there is a very important reason to do so. But if an administrator does want to change it, they can click Edit Default Values and insert their password, and then they'll be able to edit. To leave the default value page, just click Lock and Exit, and it will take you immediately back to the Global Inputs page. On the Global Input sheet is also a button that says Clear User Inputs. The user can click this button at any time, and it will clear all cells and every single sheet for every single step. Cells should be cleared before beginning any new analysis, and it should be noted that this process can take a few minutes sometimes to complete. Now, to proceed to the next step, you can now press Proceed to Step 2. For step number 2, traffic demand data, the user will enter the most recent demand data for the two-way stop control intersection being analyzed, including either turning movement counts or AADTs. This information will help the tool estimate delay times. The tool allows the flexibility to provide one of the following 3 methods for characterizing traffic demand: hourly counts, peak hour count, or AADT. The user only needs to provide data using one of these options. The user can select which of these 3 options for data entry to use by clicking the appropriate aerial button. Before doing so, the user should consider the type of data that they have available. Hourly count should be selected only if the user has 13 or more hours of turning movement counts for each approach. Peak hour counts can be used when the user has 12 hours or less of turning movement count data for each approach, and an idea of the hourly demand distribution for traffic at the two-way stop control site, or actual hourly demand distribution percentages for the two-way stop control site. The last option, AADT, requires 2-directional average annual daily traffic data for each approach, as well as percent distributions for the left, through, and right movements for each approach, and an idea of the hourly demand distribution of traffic at the two-way stop control site or actual hourly demand distribution percentages for the two-way stop control site. Again, the hourly count option should only be used if 13 or more hours of turning movement count data are available. This is in alignment with both the MUTCD as well as the standards that NCDOT uses internally. To select this option, the arrow button beside it can be chosen. When the hourly counts arrow button option is selected, a pop-up box will appear. The user is required to enter the beginning and end time of the period for the turning movement counts available. For example, if the user has 13 hours, starting at hour 6 and going until hour 18, they can enter it here with the start time as 6 and the end time as 18 and click OK. The number of rows in the detailed volume counts table will adjust to accommodate the number of hours and the time period selected by the user. For example, here you will see this goes from 6 to 18 as entered. Once the table has adjusted appropriately, the user must provide turning movement counts for vehicles per hour for left, through, and right at each of the 4 approaches. Once every yellow cell in this table has been filled with turning movement counts, the user can then proceed to the next step by clicking Proceed to Step 3, or can return to Step 1 to make further edits by clicking Return to Step 1. When 13 or more hours of turning movement count data is not available, the user can choose the peak hour count option. This option is best when 12 or less hours of turning movement count data are available. To begin using this option, click on the arrow button beside it and see the new sheet pop up. To begin using this option, the user must first select 1 hour of turning movement count data to enter into the tool for analysis, most likely a peak hour. This single hour of count data will be used to model a traffic distribution for a full day. Before proceeding to fill out the demand flow rate data table, the hour of analysis can be selected by clicking the drop-down box in the specified analysis period table as shown here. For example, we'll choose 5 as a peak time period for analysis. Then the user can go to the demand flow rate table and fill in each of the yellow cells. As shown here. This is the flow of vehicles per hour for left, through, and right. Finally, the user must populate the hourly demand distribution table, seen here, with the percent of traffic at the current two-way stop control intersection for each hour compared to the total for the entire day. Although these percentages can be manually entered, such as this, finally, the user must populate the hourly demand distribution table with the percent of traffic at the current two-way stop control intersection for each hour compared to the total for the entire day. Although these percentages can be manually entered, the user has the option to auto-populate this table by clicking the Insert Default Hourly Factor button in the upper left-hand section of the sheet and choosing the default distribution profile which best aligns with the site of interest. For example, if 2 minor equivalent peaks, a minor in the AM and a minor in the PM, as seen in this graphical image, best represents the two-way stop control intersection currently present, the user will then hit OK to populate the hourly demand distribution. In cases where the user decides that a different distribution is more appropriate, they can return to the Insert Default Hourly Factor Distribution button, click Cancel, and then return back and select a different option and click OK again. Regardless of the entry type, the final distribution in the table should add up to a total sum of 100%, as seen below. Once turning movement count data for the specified analysis period and hourly demand distribution have been entered, the user has finished step 2 and can either choose to move forward with the next step by clicking Proceed to Step 3 at the top, or can return to the previous step by clicking Return to Step 1 to modify a previous entry. The final entry option, ADT, is based on planning label data using average annual daily traffic data. This method can be useful during the early planning stages of a project, especially if the user does not have access to turning movement counts. Using this method, the user is required to enter two directional AADTs for each approach of the intersection. Two directional AADTs are the total traffic recorded in both directions along the roadway that intersects at or near the two-way stop control intersection of interest. To begin entering data using the AADT option, enter the AADT value for each approach in the demand flow rate data table. For example, next, the distribution of turning traffic for each approach must be entered in the current traffic distribution table. The user is required to enter the percentages of turns for left, through, and right lanes on each approach leg. For each leg, the sum of the total percentages of traffic should be 100%. For example, finally, similar to the peak hour count entry method, the hourly demand distribution is required to populate the traffic demand over the entire day. The most likely entry method for this will be using one of the defaults provided in the tool using the Insert Default Hourly Factor button. In the upper left-hand corner, selecting the option that is the best fit and clicking OK. Once the turning movement distribution and hourly demand distribution have been entered, the user has finished step 2 and can either choose to move forward with the next step by clicking Proceed to Step 3 or clicking Return to Step 1 to modify previous entries. Again, only one of these three options needs to be filled in for step 2. The next step, step 3, crash data, focuses on past crash data for the intersection being analyzed. For this step, the user must have the most recent 3 to 5 years of data for the current two-way stop control intersection, broken down by the standard cab code types used by the NCDOT. Before entering data, the user will select the number of years for the data they will be entering. To choose the appropriate number of years, click the number field and then type in the number for the years that data is available for. So, for example, in this case, if we have 5 years of data, we'll enter 5 next to number of years of crash data. Again, at least 3 years of crash data, preferably more, should be used. Then enter the total number of crashes experienced per year at the intersection of interest. The data entered should be broken down by fatal injury crashes, type A injury crashes, type B injury crashes, type C injury crashes, and property damage only crashes. And again, this is the total that we're entering for all 5 of the years that are available. As you can see, the tool automatically will calculate the average number of crashes per year given the data entered. Note that if there's no data available for a particular category, so for example, I have no information whatsoever about the fatalities at a site, leave that cell empty. However, if there were no fatalities and I have a value of 0, I would enter the value of 0 here. After entering all crash data, either choose to move forward with the next step by clicking Proceed to Step 4, or click Return to Step 2 to modify previous entries. Steps 4, 5, and 6 are broken down by alternative type. In the tab for each step, the user will enter 2 key sets of inputs specific to each alternative type: construction costs and geometric configuration. Users are advised to enter all inputs for each step before moving on to the next one. Before entering the configurations for each facility option in the sheets for steps 4, 5, and 6, the user should select the appropriate construction cost for each alternative. Construction costs for the purpose of this tool are the capital funds needed to convert an intersection from a two-way stop control intersection to another type, including pre-construction, such as right-of-way purchases and preliminary engineering, and physical construction, utility moves, additions, infrastructure, changes, additions, etc. When entering the anticipated initial design and construction costs for each conversion type, the user can either enter one of the default cost estimates provided in the tool or enter their own estimate. Default cost can be seen here. There are 3 different options: low, average, and high, with explanations for each. So, for example, if my area had significant right-of-way purchase required or a significant utility move that was needed, I would enter $750,000 as the construction cost. Alternatively, if I had already done an estimation for the particular site and I knew it was going to cost $800,000, could enter that value. Again, please note that there is no drop-down box for entering the design plus construction cost, and that must be manually entered and should be double-checked by the user because there is a lot of room for error there. For each of these 3 steps, steps 4, 5, and 6, the user is also required to input configuration data for all 3 facility options once the construction costs have been selected. The configuration data entered by the user in each of the alternative specific steps should be based on what the tool user and/or decision makers have determined to be the most appropriate facility configuration for the site. These geometric configuration inputs will be used with 2010 HCM methodologies to project future delays for each of the facility alternatives. Once roundabout construction costs have been entered, the user can enter the desired geometric characteristics for the associated roundabout. The roundabout lane configuration table includes the entry lane and right turn bypass configurations for each approach. The user can either manually select the configurations by clicking on the yellow cells for each approach and selecting the best option from the pull-down menu that appears, as shown here, or can auto-populate the configuration table using the tool's Geometry Designer Wizard. To use the wizard, click Launch Geometry Designer Wizard for Roundabout button here, and a pop-up screen with configurations for each approach should appear. To adjust the configuration using the wizard, select the appropriate chosen configuration using the drop-down menu. For example, if I want to add a yield lane, I can select yield here, and the image will change accordingly. If I wanted to add a lane, the same thing would happen here for the westbound direction. Examine the pictures to ensure they align with your planned configuration. Because the tool is only designed for one-lane roundabouts, the user has the option to select one of the 3 following approaches for each leg of the intersection. Again, these options are none, yield, and add a lane, just as in the manual entry in the configuration table. At any point in the process, the user can click the Discard Configuration button to develop a new configuration or to manually enter inputs into the table. Once the configuration is finalized using the wizard, however, the user can confirm the configuration by clicking Accept Configuration. Both the design plus construction cost and the roundabout configuration table should be inspected to ensure that the correct inputs have been selected before clicking the Proceed to Step 5 button. Alternatively, the user can return to a previous step to modify previous entries by clicking Return to Step 3. Step 5 is almost identical to Step 4, except it focuses on inputs for all-the-way stop as opposed to roundabout. Again, the user will need to first enter the design plus construction cost, and there are 3 options the user can choose from, each with descriptions. In this case, I'm going to enter $25,000. After entering the all-the-way stop construction costs, the user can enter the desired geometric characteristics for the planned all-the-way stop. Users will provide data for the number of lanes for each approach in the all-the-way stop lane configuration table. These can be selected as yes or no from a drop-down box. Please note that there will always be a lane 1 present. However, lane 2 is optional. Alternatively, as with the roundabout, the user has the opportunity to use the Geometry Design Wizard to select their inputs. To use the wizard, click the Launch Geometry Designer Wizard for All-the-Way Stop Intersection button. A pop-up screen with configurations for each approach should appear. To adjust configurations using the wizard, select the appropriate chosen configuration using the drop-down boxes. Again, the options are yes for a second lane or no. A new image should appear with each new configuration selection. Examine these pictures to ensure that they align with your planned configuration. Any entry of yes for lane 1 and no in lane 2, as seen here, means the approach is a shared left through right lane configuration. If lane 2 is also yes, as seen here, then there is a left turn bay present for the left turn, and the through and right are shared. At any point in the process, the user can click Discard Configuration to develop a new configuration or to manually enter inputs into the table. Once a configuration is finalized using the wizard, the user can confirm the configuration by clicking Accept Configuration. Both the design plus construction cost and the all-the-way stop lane configuration table should be inspected to ensure the correct inputs have been selected before clicking the Proceed to Step 6 button to move to the next step, or clicking Return to Step 4 to modify previous entries. Step 6, signal configuration, is very similar to the two previous steps, 4 and 5, in that both design and construction costs and signal lane configuration must be entered. To start, just like the previous steps, there is a low, average, and high option for construction cost, each with descriptions. I'm going to enter into the construction cost box here the average range, $90,000. Once construction costs for the proposed signalized intersection have been entered, the user can input the signal's geometric characteristics. Please note that because most isolated intersections in North Carolina are running under fully actuated mode, signal inputs for this step are used to calculate delay with the assumption of full actuation. In order to input the signal lane configuration, the user can either choose 0, 1, or 2 to indicate lanes for each left, through, and right movement for each approach in the table. Or they can auto-populate the configuration table using the tool's Geometry Designer Wizard. To use the wizard, click the Launch Geometry Designer Wizard for Signalized Intersection, and a pop-up screen with the configurations for each approach should appear. To adjust the configuration of lanes using the wizard, select the appropriate chosen configuration using the drop-down boxes. A new image should appear with each new configuration selection for each approach. Occasionally, as just shown here, some of the options may be infeasible based on the tool. In those cases, an error message will appear. Again, the user should enter the lane configuration as it appears at the stop bar by selecting either 0, 1, or 2 for each turning movement for each approach. 0 indicates a left or right, no dedicated lane for the turning movement. 1 for left or right indicates a dedicated turning lane for the turn movement. And 1 or 2 for through indicates either 1 or 2 dedicated through lanes, respectively. For example, an entry of 0, 1, 0, as shown here, would mean the approach has a shared left through right lane. At any point in the process, as with the other steps, the user can click Discard Configuration to develop a new configuration or manually enter the data in the table. Once a configuration has been finalized using the wizard, the user can confirm the configuration by clicking Accept Configuration. All three of the input tables for this step should be inspected to ensure the correct inputs have been selected before proceeding. The best way to do this is also to look at the images in the design wizard before accepting the configuration. Step 6 is different from the previous steps because the user cannot immediately proceed to the next step once the configurations are finalized. Instead, after finalizing all signal and construction costs and configuration inputs, the user must click the Run Analysis and go to Step 7 button in the upper left section of the page. Clicking this button is necessary to process the final outputs of the tool, including the projected value of the costs and benefits for each alternative. The user should click the Proceed to Step 5 button if they have any changes that need to be made to the inputs before the final analysis is run. Please note that the analysis process may take several minutes and may cause other computer programs to temporarily freeze during processing due to the amount of data analyzed. While the analysis is running, a pop-up box may appear notifying the user that a level of service F is projected to occur for one or more of the conversion alternatives at some point during the time frame of analysis. The user must click OK in the pop-up box to acknowledge this message and to continue with the analysis. If a level of F is projected, the user can return to the previous steps and make adjustments to the period of analysis, geometric configurations, or other inputs to address the LOS of F as appropriate. For some intersections, high levels of demand may lead to an LOS of F regardless of the geometric configurations of the facilities. In such cases, users can use the comments section of the tool's printable report to explain related recommendations. Once the analysis is complete, the user will be notified by a pop-up box. The user must click OK in the pop-up box to proceed to the results page, shown here, which will show the final outputs of the tool. One important note: anytime changes are made to inputs on any page, the user must return to Step 6 and click Run Analysis and go to Step 7. A failure to do this can result in inaccurate outputs, which defeats the purpose of using the tool. Step 7 Results provides information about the monetized costs and benefits of converting the two-way stop control to the three other alternative types. The information in this sheet includes a table that provides a snapshot of each option in the first year of analysis, including the two-way stop control, so the existing intersection as well as what one would expect to see in the first year of operation for roundabout, all-the-way stop, and signal. This table provides a simple snapshot of how applying a given alternative may change outcomes at the existing intersection. However, the data in this table is not the final output of analysis and should not be used to compare the long-term costs of alternatives. It is merely an informational table. The final outputs of analysis are presented in another table below, labeled the long-term difference between two-way stop control and conversion alternatives. This table breaks down the long-term discounted costs and benefits of each alternative based on variable type, and most importantly provides the ultimate deliverable of analysis, the net present value for each option. These net present values are the long-term benefits that would expect to be seen if the two-way stop was converted to each of the different alternative types. These outputs should be compared in order to identify the best intersection option based on lifecycle costs. They represent the benefits that the state of North Carolina can expect to gain from an intersection option. Therefore, the intersection type with the highest NPV is considered to be the best option because it will provide the greatest value in the long run. For example, in this case, the all-the-way stop control is worth more in the long run than the roundabout or signal and would be the suggested option based on the tool's outputs. It should be noted that for some conversions, user delay and the costs associated with them may actually increase due to projected level service failure F or other factors. This can vary on a case-by-case basis. In cases where user delay is increased due to conversion, the benefit of decreased delay will be a negative value, which is indicated by red text and case by parentheses, as shown here. Additionally, users and decision makers should be aware that the highest costs and benefits of a conversion are usually associated with user delay and safety. This is because the NCDOT's CAPCO costs can be in the millions, and significant delay can result in very high costs to roadway users. For example, tool tests showed that the high volume inputs typically result in high delay costs due to excessive facility congestion, and high crash data numbers typically result in significant safety benefits, and vice versa. Once the final outputs have been calculated in the result sheet, users can proceed with editing and printing the tool's report on the analysis, as explained in the printable report section. However, before proceeding to the next step, the user should pay special attention to the values in each cell, particularly looking for values that appear to be excessively high or low. If one of the values indicates that there may have been a user input error or that an input needs to be adjusted to be more accurate, the user can always return to previous steps to do so and run the analysis again. Once the user is comfortable with all of the outputs in the cells, they can click Proceed to Step 8. To be taken to Step 8, Printable Report. To create the report, the user will fill in the areas of the template highlighted in yellow, as seen here. The yellow sections of the report will allow the user to explain or clarify outputs for a given section. For example, users can explain their reasonings for suggesting a particular alternative, even if it is projected to reach a level of service of F. That would be done here. Or to explain data that may be confusing to readers. All of the color areas and lines in the entry section will disappear when the report is printed. Before hitting the Print Report button in the top right-hand corner, the user should review the report for errors or potentially confusing data. Note that the tool does not offer a print preview option. Instead, the generated document will print directly to the default printer of the user's computer once the Print This Report button has been clicked. As noted earlier, it can be clicked in the top right corner or here at the bottom of the print summary. To generate and file instead of printing, the user can set their computer's default printer to print to PDF. Once the analysis has been completed and the resulting report has been printed, the tool file should be immediately saved a final time. As previously mentioned, users are advised to include the data analysis and site name in the file name. Thank you for taking the time to use this tool.